Welcome everyone to another seminar of mathematics and high energy physics, Physics Latam. Today we are happy to have back Sunghyuk or Henry. He's currently a postdoctoral fellow at Harvard University, mentored by Professor Dan Free and supported by the Simons Foundation via Simons collaboration on global categorical symmetry. He got his PhD last year at Caltech, where he studied quantum topology and mathematical physics under the supervision of Professor Sergei Kukov. Previously, he was postdoctoral fellow at the University of Texas at Austin from August last year to this May. Today, he will be talking about spectral networks and Skein modules. His area of interest lies in studying geometry and algebraic structures inspired from physics. Today, he will be talking about spectral networks, as I mentioned, and I hope you enjoy it, and I leave you with Henry.
Okay, thank you very much for the introduction, and thanks for the invitation. I'm very happy to be speaking in this seminar. Yeah, so today, I wanted to talk about spectral networks and Skein modules. Here are some snapshots of what this talk is going to be about. Here's some figures. These are some of the figures we'll see on the top. So I wanted to make this a very expository, introductory talk, mostly about spectral networks, which are some geometric objects introduced by Gayotomori and Naisky in their study of four-dimensional supersymmetric quantum field theories, and that turns out to be closely related to a lot of areas in mathematics and physics, in particular, Stokes phenomena, resurgence, exact WKB method, abelianization, etc. So you can think of this talk as an introduction to what these words mean. And I'm not sure if I'll have enough time to get to the end, but if I do, I'll also mention their application to low-dimensional topology, especially to the study of Skein modules, which are certain interesting invariants of three manifolds. So this is a rough plan. Part one, which is going to be, I think, the most part of this expository talk is going to be about, is on geometry of Stokes phenomena. And for the most part, the quintessential example is the area integral. So we'll follow this specific example and see how these different phenomena arises. And then I'll talk about Schrödinger equations with polynomial potential, for which the area equation is an example. And then explain the exact WKB method, which is a method of solving the Schrödinger equation. And that in turn gives rise to the spectral network, which is the main object I wanted to introduce in this talk. So and this part one of this talk is largely based on Andy Naisky's lecture notes. And then if I have enough time in the end, I will move on to some of its applications, which I just called the geometry of abelianization here. There's a class of quantum field theories that you can geometrically engineer by compactifying, by starting from some higher dimensional quantum field theory, compactifying it on some manifold. And then it's known that if you start from that theory and then you go to low energy, then the low energy theory is described by basically the same type of theory, but where if you started from, say, a stack of n number of branes wrapping some manifold, then those branes split to form some n-fold branch covered. That's what I call the splitting of branes. And this, basically, it's a process of spontaneous symmetry breaking that abelianizes the theory, and this process is captured exactly by the spectral network. And as a particular example, those spectral networks, if I get to explain this in time, the spectral networks can be used to study Skein modules, and in particular, one can start from a non-abelian Skein module and map it to a abelian one. This is the so-called quantum UV-IR map studied by Andy Knightsky and Fei Yan. And then there's a way to think of them in terms of open topological strings. So if time permits, I'll get there, but if I don't, that's okay. And yeah, by the way, I wanted to make this talk very introductory. So if you have any questions, don't hesitate to ask. Just don't hesitate to interrupt at any point. Okay, so part one. So the general picture is the following. So this is so let's say we have some quantum field theory and we want to analytically continue it. By that I mean, for instance, we start from Chern-Simons theory and we want to analytically continue the coupling constant. So the basic setting is the following. Let's say this capital X sub C. This capital X sub C is the complexified space of fields. And this capital S would be some function, some complex, some holomorphic function on this space of fields. Let this be the complexified Euclidean action. So that the analytically continued partition function is given by this path integral, the familiar path integral, but we're integrating over some half-dimensional cycle inside this complexified space of fields. Well, there are many choices of this half-dimensional cycles. Well, as long as this integral converges. So for convergence, we need some condition on this half-dimensional cycle. For instance, we want e to the minus s over h bar to decrease exponentially as we go off to infinity. So that imposes some condition on the boundary of L off to infinity. And it turns out that for any critical point of this action functional, so call it x sub alpha, there is a natural choice of cycle, which I will denote by L sub alpha, called the Lefschetz thimble. So the way it is defined is, so it is the union of all the descending Morse flow lines starting from this critical point. Oops. It's the union of all the descending Morse flow lines with respect to the real part of the exponent, which is minus of s divided by h bar. So notice that h bar was a complexified coupling constant, so it can have any argument. And as we vary the argument, this real part is going to change. So this is a cartoon picture of the left-just thimble. Yeah, x alpha is the critical point, and this cone-shaped figure I drew here is a cartoon picture of the left-just thimble. It's the unit of all the descending Morse flow lines from x sub alpha. And if we project this left-just thimble down to the complex plane by applying the action, then that would be a ray. Simply because we, by definition, the left-just thimble was the union of descending Morse flow lines, and yeah, so the image would be a ray, and it's a ray starting from the classical action of that critical point, plus a ray emanating out of that classical action with an angle, which is the argument of h bar. So for each left-just thimble, we have this path integral that we defined earlier, and we can compute its asymptotic or perturbative series, that is some formal power series in h bar, using the standard techniques of Gaussian integrals and Feynman diagrams. So that is, if, say, this action s of x is given by, say, some polynomial, we've just separate out the free term, which is the quadratic part, and then higher order terms, which are the interacting part. We expand the interacting part to power series and do the Gaussian integral. So in that way, for each critical point alpha, we will get a perturbative series, so a formal power series in h bar. And it's only asymptotic, meaning in general, as long as our quantum field theory is not a free theory, as long as there's interaction term, the number of Feynman diagrams grow factorially, and as a result, these coefficients, a sub n, also grow factorially. They grow like roughly of the order of n factorial. And by simple ratio tests, this tells us that the radius of convergence of this power series in h bar is 0. So it's never convergent. It's a divergent series. But yeah, this path integral z alpha associated to the left-just thimble L alpha, this is supposed to be an actual function of h bar. So the question that arises many, many times, like in different areas of math and physics, is how do we make sense of such a divergent series? And the technique of making sense of this divergent series is sometimes called resurgence. So I'm going to be describing the main package of resurgence. The first important piece of technique is Borel transform. So let's say we have some formal power series in H bar. Say call it f of H bar with coefficients a sub n for the nth term. Then we define the Borel transform of this formal power series to be a new power series, call it Bf of psi, and define it to be this formal power series. So that is, it's basically the same formal power series, except that we divide the nth coefficient by the n plus first, by the value of the gamma function at n plus 1. So for instance, when n ranges over natural numbers, then since gamma of n plus 1 is just n factorial, we're just dividing a sub n by n factorial. And by doing this, by taking this ratio, we're getting rid of the factorial divergence. So this new series is going to have a much better convergence than the one we started with. In general, this power series we started with, in general, n doesn't have to range over natural numbers. It can be, say, half integers or something else. And in those cases, we can still apply this Borel transform, and then the exact value of this gamma function will be slightly different. Let's suppose that the original series, f of h bar we started with, is convergent. So in this case, like whatever we do, at the end of the day, we want to get the same function. If we started from something convergent, then we need to get the same function. But we're trying to come up with a device which can also apply to divergent series and gives us something convergent. So yeah, so suppose that f is a convergent power series in h bar. Then, so we apply this Borel transform that I just described up here. And then we take this integral, which is a version of Laplace transform. So here we are integrating over this new variable psi. Oh, here's a question.
Sorry for interrupting. So you mentioned that for the resurgence process, the summation set could be taken a little broader. Can we take it to be integer? But if we were taken to the integer, then gamma function is not defined for like.
Oh yeah. I guess what I said is when n is a natural number, that is if it's at least 0, say non-negative integers, then gamma function makes sense.
Yes. But can we extend it somehow to integers or?
Oh, you wanna extend this to, say, n like negative integers.
Negative infinity positive. I don't know, like Laurent series.
Yeah, in that case, this gamma function would have poles, so this naively wouldn't make sense.
Sorry, just forget about it.
Yeah, I don't know. That there might be a way to make sense of it, but let's say for the purpose of this talk, we only assume n to be non-negative. Thanks for the question. Okay, so we started from a formal power series. We applied the Borel transform, and then we take this integral over psi, integral of this Borel transform multiplied by exponential of minus psi over h bar. And we integrate along the ray with angle equal to the argument of h bar. And say, multiply everything by 1 over h bar in the end. And this is a simple exercise. You can basically check it term by term. That if you do this, if you take this form of Laplace transform of the Borel transform, you get back your original series. So in this sense, this Laplace transform is an inverse Borel transform. So there's an inverse transformation that allows us to get back the original function, original series. So like, if we're getting back the original series, then what's the point, right? The point is this last expression often makes sense even when the power series we started with is factorially divergent. So in some, often this this right-hand side will make sense as something analytic in h bar for some values of h bar. And yeah, in this, so this last expression is called the Borel summation of f. So this is a way of making sense of a divergent series. So yeah, so the point is, so we have this perturbative version of partition function, and we can apply this Borel resummation. And we can often compute this non-perturbative partition function using this. So at this point, you might be wondering, why do we need to take this particular form of Borel transform? Why not, divide by something that is even bigger than n factorial, and then this new series would have an even greater chance of converging. So why this particular form of Borel transform is a natural thing to do. Yeah, so let me tell you a little bit about the geometry of Borel transform. So recall this picture of the Laplace thimble, which I've been denoting by L sub alpha, where alpha or x sub alpha is a critical point. S sub x sub alpha is the critical value or the classical action. And then it projects down to this ray. And so for a point small s in this ray, let v sub alpha of little s to be the intersection of the pre-image of this little s under the action functional intersection with the Laplace thimble L sub alpha. So yeah, in this picture, that's exactly the fiber over this little s. And this is often called the vanishing cycle. So, well, mathematically, it's gonna be a cycle representing a half-dimensional homology class in the pre-image, this big S inverse little s. And it's called a vanishing cycle because as we move this little s along this ray and move it closer and closer to this critical value, big S of x sub alpha, then the cycle will shrink, and in the end it will vanish. That's why it's called the vanishing cycle. So yeah, in this picture, what we can do is, so we have this partition function z sub alpha, which is a path integral over the leftist thimble. But let's try integrating along the fibers first. Remember, the fibers are exactly what we call the vanishing cycle. So once we integrate along the fibers first, then what we're left with is just the ray. So this is the ray, this ray in the complex plane. And this action functional will be simply e to the minus little s over h bar, because we're fixing this little s in the base, multiplied by the volume of the vanishing cycle, and then we're integrating over points on this ray. And then we can do a simple integration by parts. Yeah, so this integral is in the form of product of this first factor and the second factor. So doing the integration by parts, we get this last expression. And notice how this last expression looks very similar to this expression of Borel resummation. So if you compare this expression of Borel resummation with this expression, then you see that this integral inside this parenthesis must be equal to the Borel transformation of the perturbative series. So this thing in this parenthesis is an integral starting from the critical value or the action or the classical action up until some point in the ray, which we call S, and we're integrating the volume, which means it is just the volume of the leftist thimble with cutoff. We're choosing a cutoff point S rather than, so instead of the whole leftist thimble, which goes off to infinity, we're choosing a cutoff and taking the volume. So as I just said, comparing this last expression with the Borel resummation, we conclude that the volume of this leftist thimble with cutoff must be equal to the Borel transform of the perturbative series, which is this expression. So this tells us why Borel transform is important, and this gives us a geometric way of thinking about it. Or equivalently, by taking derivative with respect to S, on the left-hand side, we just get the volume of the vanishing cycle. On the right-hand side, we get a slightly different expression. So by taking the derivative with respect to S, that just lowers this power n to n minus 1, and then this gamma function becomes gamma n instead of gamma n plus 1, which can also be expressed as the Borel transform of 1 over h bar times the perturbative series rather than the perturbative series itself. Yeah, maybe it'll be in case I was going too fast or it wasn't so clear, maybe it, I should give you an example and maybe it'll be clear what's happening here. So let's say our action is given by x cubed divided by 3 minus z times x, where z is just some parameter. Then by taking derivative, which would be just x squared minus z. So we see that the critical points are the 2 points plus minus z to the half. And so by re-expressing x as this, by just rewriting x as the critical point plus some other number, we see that this action functional can be written as the classical action term plus some quadratic term plus the interaction term. So notice that the interaction term is always 1/3 times x cubed. And the quadratic term has the coefficient plus minus z to the half, which depends on the choice of the critical point. And we have this classical action. And then it's a relatively simple exercise. I wouldn't go into the detail, but yeah, once you have this, by expanding the exponential of the interacting part into power series and then doing the Gaussian integral, we can compute the perturbative series associated to the two critical points. So this is the end result. And here C, what I denote by C is exactly the coefficient of the quadratic part, the coefficient of the free part of this action functional, which was plus minus z to the 1/2. Yeah, and on the other hand, we can also try to compute the volume of the vanishing cycle. But notice that right now we have a one-dimensional integral, which means that for each choice of this little s, the point on the ray, its vanishing cycle, its pre-image, is going to be just 2 points. And we can compute the 2 points by solving for x in this equation. If you solve it, those 2 points can be expressed as this power series is an s to the half. And then the volume of the vanishing cycle will be just the sum of weights of the 2 points, which is 1 divided by the derivative of the action at one of the points of the vanishing cycle minus 1 over the derivative of the action functional evaluated at the other point of the vanishing cycle. If you do this calculation, you get some power series in S, and it can be packaged into this simple formula. And notice the similarity of this formula, this end result, with the perturbative series we had up there. The only difference is this gamma of m plus 1/2 in the denominator, and that this exponent of h bar, which was m plus 1/2, now became m minus 1/2. So in other words, this end result is simply the Borel transform of 1 over h bar of the perturbative series we had above. And this is exactly what I told you earlier, that this Borel transform gives us exactly the volume of the vanishing cycle. Yeah, I mean, so this connection between the Borel transform and the volume of the vanishing cycle, probably not so useful, but I thought it's a just nice way to think about Borel transform, like why it's a natural thing to do, like why it comes from geometry. So I wanted to tell you a little bit about this and this example. Now, here are some important remarks. So this Borel resummation, I said often it makes sense even when the formal power series we started with is divergent. But there's a subtle point, which is that it is as we vary the argument theta of h bar, the coupling constant, at some point there might be a Morse flow line with respect to the same Morse function, the real part of the minus of the action s divided by h bar between critical points. And across those angles, or across those rays, the Borel resummation will jump. So this is a simple cartoon picture of that. So let's say x sub alpha and x sub beta are 2 critical points of our action functional. And these 2 lines are, say, these are the downward Morse flow lines. And so these are the left chest thimbles in this picture. But as we vary theta, these left chest thimbles will move around, but at some point, there might be at some specific value of theta, which I denoted by theta sub c, and called the critical phase. There might be a Morse flow line from one critical point to another. And then as we passed that critical phase, now the left chest thimble will become disjoint again, but then the left chest thimble for x alpha will now live in a different relative homology class than it started from. So that is the relative homology class of the left chest thimble L alpha can jump across some critical phase where there is a Morse flow line from x sub alpha to some other critical point x sub beta. And as a result, the path integral associated to this left chest thimble L sub alpha will also jump because this relative homology class jumps. And this is known as the Stokes phenomenon. When this jump happens, basically the relative homology class for L sub alpha picks up some integer multiple of the relative homology class for this other critical point for which there is a Morse flow line from alpha to beta at some critical phase. And those rays, which correspond to these angles of the critical phase, are called the Stokes rays. that is, Stokes rays are where those jumps can happen. And because of the Stokes phenomenon, this Borel transform is only going to be defined away from Stokes rays. So, yeah, so this is a typical picture. So remember the Borel transform of some formal series in H bar. It's a new series in Xi. So this is the Xi plane. This little dot in the middle is the origin. This Borel transform is going to have better analytic property than the formal power series we started with, but still it can have a number of singularities. And the point is that those singularities, which I drew as these small red X's, those singularities will occur exactly in those Stokes rays. So, okay. In other words, remember that, okay, what's Borel ray summation? We first take this Borel transform. And then we integrate along this ray of some angle. So if this is a picture of singularities of the Borel transform, then, you know, along those rays we can integrate. Along those rays, and we can integrate. But at some point, like right before it crosses those singular point and after, the resulting Borel ray summation will jump. And that's exactly the Stokes phenomenon that I described here. And it turns out that those jumps across Stokes rays are determined by the Borel transform of some other perturbative series that is associated to some other critical point. So in this way, those perturbative series for one critical point, it talks to one another, and this phenomenon or this whole package is called the resurgence.
Why is the condition the beta should be different than alpha?
Oh, yeah, so, well, okay, so what is the jump? If you look at this picture, for instance, so we started from a path integral over L alpha, the leftist symbol for spherical point alpha. As we go across the Stokes line, the homology class of L alpha now picks up some multiple of homology class of L beta for some other beta. And that beta is the other critical point for which there is a Morse flow line from alpha to beta on that Stokes line. So we have this relation. In other words, the path integral over L alpha will jump because it picks up this extra homology class, and the amount it jumps will be determined by the path integral over L beta, over this other leftist symbol. Yeah, so maybe to be more precise, like what I meant is determined by beta, and that beta is exactly this beta in this picture. Yeah, I said various beta because for different Stokes line, there can be many different betas. Yeah, but once you fix a singularity in the Borel plane, so okay, the position of the singularity in the Borel plane is determined by the instanton action. Yeah, okay, maybe let me just say that the position of those singularities, let's say the singularity on top is okay, so where were we? Yeah, let's say the singularity was responsible, let's say x beta is responsible for the singularity, then this position of the singularity is really the instanton action, which is which is the difference between the two classical actions. Yeah, anyway, that's the beta. Yeah, this guy. Let's move on to, let's turn our attention to complex ODEs now. And we'll focus on Schrödinger equation with polynomial potentials, which is this equation. And we want to solve for psi. Oh, here, P of Z is some polynomial in Z. And probably the simplest example is the Airy equation, which is the case when this polynomial is just Z. And it's called the Airy equation because it satisfies, for instance, it's easy to see that if we start from the Airy integral, I showed you earlier, that satisfies this differential equation. Okay, so given such a complex ODE, how do we solve for psi? Or in other words, since this is a degree 2 ordinary differential equations, there's going to be a two-dimensional space of solutions. Yeah, so the question is to determine mathematically the rank 2 local system of solutions. WKB method tells us we can solve it perturbatively, and it goes as follows. So we start by introducing a new parameter h bar. So yeah, and consider this slightly modified Schrödinger equation. So h bar equals to 1 corresponds to the original Schrödinger equation, but now we're introducing this new parameter. So I guess one can think of it as we're considering a whole family of differential equations instead. And as an ansatz, let's write psi of z and h bar, because now our new equation depends on h bar as well. Write it as the exponential of 1 over h bar times the integral starting from some point z0 to z, an integral of some one form denoted by lambda of h bar. Yeah, for some holomorphic one form, lambda of h bar. And so we can plug this into our equation and then solve for this holomorphic one form. And we can do this perturbatively. And this is what the WKB method is. So we first write lambda of h bar as a formal power series in h bar, whose coefficients are some holomorphic one forms. So which I denote by lambda sub n for the nth coefficient. And then we can recursively solve for lambda n's. So if you plug this expression in to this Schrödinger equation, then the first term, you get y dz, where y is some square root of minus of the polynomial potential. And then the subsequent terms, you can solve them recursively. The second term is given by some rational function, that is the derivative of p divided by p dz, and then the next term looks like this, etc. And notice the appearance of those square roots. So that means these holomorphic one forms, they're more naturally defined in some branched double cover rather than the complex plane we started with. So it is natural to consider the following Riemann surface called the spectral curve, which is just the collection of those y's and z's, where y is one of the square roots of minus the pz. If we forget about y, then this just maps down to the complex plane of z's we started with. And this is a 2-to-1 branched cover, branched at zeros of this polynomial pz. Yeah, this is a cartoon picture. Yeah, we can think of C as sitting in CP1, and infinity is some puncture or irregular singularity. Then sigma. Yeah, this is a cartoon picture of this branched cover, this double branch cover, sigma over C. The branch points are exactly the zeros of this polynomial pz. This spectral curve carries the natural holomorphic one form, lambda 0, y dz. And also the formal holomorphic one form that can be computed using this WKB method. They're all naturally holomorphic one forms living on the spectral curve. Okay, so we have this formal holomorphic one form living on the spectral curve. And it's so formal and basically the same theme as before. Like, how do we turn this formal series into an actual one form? As you might have guessed, and as you've just seen before, we can use Borel transform and Borel resummation. And that's what exact WKB method tells us. In order to describe the Stokes phenomena precisely, it's going to be useful to introduce the notion of the spectral networks. So let me do that first. First of all, let's let omega be some locally defined holomorphic function, which is an antiderivative of this holomorphic one form lambda 0 on the spectral curve. So that is d of omega is lambda 0 locally. And this omega, this holomorphic function, is sometimes called the action coordinate. For the reason that's going to be clear soon. Let's define the theta trajectory on sigma to be a path on this spectral curve, along which the imaginary part of e to the minus I theta times omega is constant, and the real part of e to the minus theta omega is decreasing. In other words, it's just the downward Morse flow line with respect to the real part of omega with slightly rotated angle. And you see, for this reason, omega plays exactly the role of the action in the previous part of this talk. Now, these trajectories induce a one-dimensional foliation of the spectral curve, the branch double cover, and an unoriented one-dimensional foliation downstairs. It induces an unoriented one-dimensional foliation on the Riemann surface, which is the base. I guess in our case, it's just C. And this one-dimensional foliation is called either theta foliation or WKD foliation. Yeah, and near a simple zero. So, okay, generically, this one-dimensional foliation is going to look very boring. At a generic point of C, it's just going to look like this, it's a decomposition of the plane by these lines near a generic point that is away from that is away from the branch points, but near the branch points, which are zeros of this polynomial PZ, this foliation looks slightly more interesting, and it looks like this picture. So this little red X is a branch point near which our holomorphic one form lambda 0 looks like plus minus square root of z dz. And then if you follow this definition of theta trajectory I just gave you and draw the foliation, then that looks like this picture. So there are 3 leaves of foliation that are kind of singular in the sense that they end on this branch point. And the rest of them, they are just kind of, they look like generic leaves. They go in both directions indefinitely. Now here comes the definition of a spectral network. So the spectral network is simply, okay, in this setup, it is just the union of all the critical leaves. And by critical leaves, those leaves which end on a branch point, these three blue lines that I just drew, these are the critical leaves. So, for instance, if our polynomial potential was something like minus z, then the corresponding spectral network at angle theta equals 0 just looks like this trivalent graph in the complex plane. And this is the same picture as this picture above. The picture will look slightly more interesting if we consider some higher degree polynomial potentials, such as z cubed minus 1. So this guy has 3 roots, the 3 roots of the third roots of unities. So it has 3 branch points, and correspondingly, the spectral network looks like this picture. So you see that around each branch point, there are 3 singular leaves or 3 legs coming out, and then asymptotically, they're pointing toward one of the 5 directions at infinity. Okay. With this definition alone, it may not be clear, like, why do we care about them? Like, why? What is it good for? The point is, as you'll see, the spectral network is exactly the set of z's for which the ray in angle theta is a Stokes ray. To explain this, let me define this notion of WKB soliton. So for a choice of a point z in C and a phase theta, a WKB soliton with phase theta over z is a theta trajectory on the spectral curve, which begins and ends at distinct points of the pre-image of z in the spectral curve. So for instance, in this picture I drew here, if z is a point in C, and let's say I and j are the pre-images of z in sigma, then a WKB soliton would look something like this orange line upstairs. So it's a theta trajectory, but since this theta trajectory has to go from I to j, at some point it'll need to go around the branch point. And downstairs, this WKB soliton is gonna look like an interval which starts from z and ends on a branch point. So notice that means that z must lie in one of the singular leaves of the theta foliation, which means that WKB soliton, so for fixed z and for generic phase theta, there will be no WKB solitons, but for special values of theta when Z lies on the spectral network, there's going to be a WKB soliton. We can also define the period of the soliton, say call this soliton B. Then the period of the soliton is the integral of this canonical one form lambda 0 along this trajectory B. And since lambda 0 is the derivative of the antiderivative, which we call omega, the action coordinate, this integral is just going to be just the difference between omega I and omega j. So this is really like the instanton action, the difference between the two classical actions. And this period, the argument of this negative of the period is going to be exactly theta by this construction. So for instance, in the Airy equation example, when this polynomial potential is minus z, then one can check that for any non-zero value of z, there are exactly two WKB solitons, that is, and that they exist only at those phases theta equals the argument of plus minus z to the 3/2. Notice that this plus minus z to the 3/2 were exactly the they were exactly the critical points of the Airy action that we saw earlier. And this is the periods. This is exactly the difference between the critical values or the classical actions of the two critical points. And one can check that a point Z is in the spectral network if and only if there is a WKB soliton with phase theta over Z. So in other words, spectral network encodes whether there is a WKB soliton or not over that point Z. And the conjecture, or say, has been that there's, I mean, to be safe, it's stated as conjecture, but something that's been checked over and over again in a variety of examples, is that so we used WKB method to get a formal one form on the spectral curve. We applied the Borel transform, and then this conjecture says that this Borel transform admits an analytic continuation to the star-shaped region around 0, which does not contain any periods of WKB solitons beginning at P. In other words, the singularity of this Borel plane occur exactly at the periods of the WKB solitons. So as long as we avoid those singularities, say as long as we do Borel resummation along the rays that avoids those singularities, it's going to be Borel resummable. And as we go across those Stokes lines, there will be jumps. So in short, this formal series can be Borel resummed at a point P in the spectral curve to give an actual holomorphic one form, lambda of H bar, except when the argument of the coupling constant is the phase of some WKB soliton beginning at P. And as a result, over any simply connected domain outside of the spectral curve, outside of the spectral network, we get two canonical solutions up to scaling, which are the end results we get by using the exact WKB method. The exponential of 1 over h bar of the integral of the actual one form we get by applying the Borel resummation of the formal series we get from WKB method. And we get two canonical solutions because for each point z, there are two pre-images in the spectral curve. So for each of them, we get two canonical solutions like this. And this gives, so we start from the solution to this ODE. So you can think of it as a rank 2 vector bundle. But then here we're getting two canonical solutions up to scaling. So we're getting a rank 1 vector bundle over the spectral curve away from the branch points. So this gives us a stratified abelianization. This is an example of an abelianization that I mentioned at the very beginning. Stop. Okay, this is the end of part 1. Are there any questions? Do you want to take a 10-minute break?
Yeah, it's up to you.
Okay, yeah, well, why don't we take a 10-minute break and then we'll do part 2. Okay, welcome back from the break. I don't know how much like I don't know if all of you were able to follow the part 1 of the talk, but I hope I gave you some idea of what spectral network, resurgence, Stokes phenomena, and all these business is about. Even if you didn't fully understand it, I hope I gave some idea. So in the remaining half an hour, I'll try to breeze through and just give you some idea of like what, like how we can apply spectral networks to low-dimensional topology. So I myself I consider myself as a low-dimensional topologist, and this is the part, for me at least, this is where all the fun is. So let's say Y is an oriented 3-manifold. Then there's an invariant of this 3-manifold, which we call the Skein module. So let me introduce it. The GLN Skein module of this 3-manifold Y is the vector space over, say, the field of rational functions in Q, spanned by the spanned by the ICTP classes of frame-oriented links in Y and modulo Skein relations. And here are the three Skein relations. So, okay, what does it mean by Skein relation? Well, okay, if we have a triple of length, say, that looks exactly the same away from a small ball, and inside the small ball, the intersection of that small ball with the link, with one of the link, looks like this leftmost picture, and say that intersection with another link looks like this picture. And let's say the intersection with the last link looks like this picture. Then whenever we have such a triple of links, we impose this linear relation among those vectors in this vector space. So that's the first relation. Second and third, yeah, these are kind of similar relations. So remember, we're talking about framed links. So, and we're assuming all the drawings are in the blackboard framing. And so whenever we have this kind of picture, some sort of kink in the link, we can remove it, and then at the cost of getting this extra factor of q to the n. And if we have an unknot, we can remove that unknot, and at the cost of getting this extra factor, q to the n minus q to the minus n divided by q minus q inverse. If you are familiar with Chern-Simons theory and Wilson line operators inside them, they give link invariance, and turns out these Skein relations are obeyed by those Wilson lines. So yeah, you can think of this as some sort of a space of Wilson lines, expectation values. It turns out the Skein modules are also relevant to the Hilbert space in Caboose-Witten theory, but that's another story. Okay, anyway, this is some interesting invariant of this three manifold. Yeah, here I'm just mentioning that there is, so gel n, it depends on this choice of rank n, and there's also an upgrade of them that kind of interpolates all these gel n Skein modules, and that's called the Hopfli PT Skein module, defined in basically the same way. It's spanned by framed-oriented links, modulo Skein relations, but Skein relations are slightly modified. Now, instead of q minus q inverse, we have z. Instead of q to the n, we have a. And so it interpolates all the gel and Skein modules in a sense that by making this specialization, we recover the gel and Skein module. Yeah. So anyway, these are object of interest. Yeah, understanding Skein models better. And okay, there can be many different reasons why we care about Skein modules. One good reason would be that Skein modules give quantizations of the character variety. That is, if we take the gel and Skein module and take the classical limit, that is, if we set q to be 1, then, so notice that in this gel and Skein module, one of the Skein relations was this one. And notice that when q is equal to 1, this right-hand side vanishes, which means that we can just, whenever we have crossing of a link, we can freely just cross it, because an overcrossing would be equal to the undercrossing. when Q is equal to 1. Which means whenever we have two links in Y, we can just superpose them in any way we want. And that gives us the product structure, because it doesn't matter how they link. Because when Q equals to 1, the linking doesn't matter. We can always cross one strand across another. So when Q is equal to 1, the Skein module becomes an algebra, which turns out to be isomorphic to the algebra of functions on the gel-end character variety. That is the space of gel-end flat connections on Y. Yeah, and of course, flat connections they appear everywhere in math and physics, important objects. For a bit of physical context, and another reason why these Skein modules are, why you might be interested in Skein modules. There are these four-dimensional supersymmetric quantum field theories with n equals 2 supersymmetry, known as theories of class S. These are theories labeled by a pair, where C is some Riemann surface, G is the algebra or a root system. Let's say we take GLN for it. And so we'll denote this theory by T of C with superscript G. And as I briefly mentioned at the very beginning of this talk, in physics, as we go from high energy to low energy in those theories which are kind of geometrically engineered, so this GLN theory can be thought of as a theory coming from n number of branes sitting on, like, wrapping C, this Riemann surface. And as we go from UV to IR, those branes split and form an n-fold branch cover over C, which I denoted by C tilde. And then the resulting theory, even though we started from a non-abelian theory, the resulting theory becomes abelian. It's a theory based on GL1. Yeah, you might have seen something similar in the context of Donaldson-Witten theory, which is a high energy theory, and which in low energy becomes effectively the Seiberg-Witten theory, which is an abelian theory. Yeah. And by the way, this choice of branched cover, this is a choice of vacuum in the IR, sometimes called a choice of vacuum in this Coulomb branch. Anyway, what I wanted to say is that putting these four-dimensional theories on certain background, which is basically R4 with some omega background. It's fine if you haven't heard of this terminology. But the point is that it turns out that the algebra of line operators in this theory is the Skein module of this Riemann surface, C times R. So what kind of intuition do we gain from this? Well, it is that as we flow from UV to IR, there should be a corresponding map of line operators. And I just said that the line operators form the Skein module. So mathematically, there should be a map from the GLN Skein module of this Riemann surface times R to the gel1 Skein module of this new Riemann surface, C tilde, the n-fold branch cover, times R. Simply because, as I said, as you go from UV to IR, the IR theory is based on the n-fold branch cover, and it's based on the gel1 instead of gel-n. So there should be such a map of line operators, which can be thought of as a quantum version of the abelianization of flat connections, in a sense that Skein modules quantize the character variety. And this is indeed what Andy Neitzke and Fecha did in their work. And they, in case of double coverings, that is when n is equal to 2, they explicitly constructed this map called the quantum UV-IR map using spectral networks. So yeah, I have about 20 minutes left, so I guess my goal is to tell you a little bit about this map. Okay. So we're trying to construct this map of Skein modules, gel-n Skein modules of Riemann surface times R, the gel-1 Skein module of some n-fold branch cover, but let's say we specialize to n equals to 2, so it's a branch double cover, similar to what we saw in the context of the exact WKB method. And the way this map is going to be defined is the following. Let's say K is some link in K is some framed oriented link in C times R. And look at this class in the Skein module. And we're going to map it to some linear combination of what I call lifts of K, which I'll explain in more detail in a bit. So we're summing over lifts of K. And these K tilde are links in C tilde times R. So they represent some class in this gel1 Skein module of C tilde times R. And it's a linear combination. So there's going to be some coefficients. Let me denote them by C A tilde of Q. And yeah, these are just some weights or some coefficients. They're going to live inside some Latam polynomial ring. Q. The point is, okay, why is this relevant to spectral networks at all? The point is that the spectral network determines all possible lifts. So let me tell you a little bit about how this works. Okay. So recall we had this thing called WKB foliation. So just to remind you, let's say C is a Riemann surface. Say with some punctures. Oops, there's a question.
Yeah, I can read it for you if you want.
Yeah, I read it. Which dimension is this Y and
I think it's Jan Mills theory, or is it Chern-Simons theory?
oh, well, okay. I wasn't talking about Yang-Mills or Chern-Simons. Yeah, I mean, you can think of this map, this quantum UV-IR map from the perspective of Chern-Simons theory. That is possible. And from the point of view of complex Chern-Simons theory. Yeah, but the way it was originally motivated from physics, and the way it's written by Skein is from this perspective of class S theories. These are four-dimensional n equals to supersymmetric quantum field theories, putting on certain background, has line operators which form an algebra that turns out to be the Skein module of a surface of this Riemann surface times R. And as we flow from UV to IR, the UV line operators will map to certain IR operators. And that's exactly what this map between Skein modules is describing. Yeah. I guess it might be a little confusing if you're seeing this for the first time, because Skein modules are defined for three manifolds. So C was a Riemann surface. But they describe line operators in a four-dimensional theory. Okay. Okay. Let's say C is a Riemann surface with some punctures. I don't know. Just to give a simple example, something like S2 with some 4 punctures. And let tau be an ideal triangulation. See? Okay, maybe I'll do a different example. Let's say C is a torus with 1 puncture, which you can think of it as squaring the 4 edges of the square, but the vertices correspond to the puncture. And tau is something like, it's an ideal triangulation, meaning we're cutting the surface into triangles whose vertices are the punctures. So, for instance, we can give a triangulation of this punctured torus into 2 ideal triangles, something like this, for instance. And there's an associated WKB foliation, which is putting 1 branch point at the center of each ideal triangle. And then we just draw, and then just claim that the spectral network looks like these 3-legged things in each ideal triangle. And then we fill in this foliation by these lines connecting these punctures. So in other words, from an ideal triangulation, we get both the WKB foliation and a branch double cover C. I see tilde, yeah. Okay, in this setting, so we want to lift our link K, living in C times R, to some link living in this branch double cover using the spectral networks or these WKB foliations. And the way it works is the following. So let's say this is our link. This is part of our link. Then we can lift it directly to one of the two sheets of the covering. Say I is choice of the sheet. And another possibility is when maybe I should have used different color. Let's see. Let me just use black for our link. And let's say our link intersects a singular leaf at this WKB foliation at some point. So since our rim surface is crossed with R, really there's an R family of the branch locus. So this red line is the branch locus. And let's say there's a singular leaf of the WKB foliation that meets our link. Then we can lift our link to this link that goes around the branch locus. Finally, if there is a leaf of the foliation that intersects our link twice, something like this, then we can lift it to the following link. So yeah, I should really label the orientation of these foliations and the sheet that these lifts live in. So this part of the link lives in the ith sheet, this part of the link lives in jth sheet. So these are the local pictures of 3 possible lifts. And so as you can see, these possibilities, I know I'm kind of rushed, so I didn't explain to you very clearly, but the point is, these are described, these are determined in terms of this WKB foliation. They completely determine what are the possible lifts, thereby determining the set of K tildes in this map. Unfortunately, the spectral network itself doesn't really tell us what these weights should be. That's a different problem. And in this work of Nainsky and Yan, so they kind of outlined the general structure of this, what this quantum UV-IR map should be for any n. But then the combinatorics gets very complicated for higher n, and at the end of the day, they were only able to define this map when n is equal to 2. So these, and the way they determined these weights is by imposing consistency relations. That is, that this map should be well defined in a sense that if we isotope K, that shouldn't change the map, and also that it should respect the Skein relations. And from the consistency relations, we can bootstrap these weights. So that works fine in n equals to 2, but then the combinatorics gets very complicated for higher n. So that's an open question. So, and yeah, and that's something that I've been working on for quite a while now. And the new kind of perspective coming from like, thinking of these in terms of counts of open topological strings, right, really helps us better understand these, how to determine these weights. Yeah, but that's the topic for another talk. Yeah, I think this is a natural stopping point. Yeah, thanks for listening. Are there any questions?